Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond. You're watching NASA TV.
Since the dawn of time, mankind has sought an answer to an undying question. Are we alone? Now, humans possess the technology to solve this mystery, and we will shift their gaze to the stars. This is the search for exoplanets. This is TESS.
From NASA's Kennedy Space Center in Florida, you're watching live coverage of the Transiting Exoplanet Survey Satellite, or TESS, a mission to find new planets outside of our solar system that could support life. Hi, I'm Marie Lewis. Thanks for joining us. TESS will help us answer an age-old question. Are we alone in the universe? The images TESS will capture could be the key to solving the mystery. TESS is a planet hunter, about to embark on a 2-year mission to scan almost our entire sky by breaking it up into 26 different sections. Powerful cameras on TESS will stare at each zone for about a month, monitoring more than 200,000 stars and looking for changes in their brightness that signal a planet crossing over. Our goal is to find other planets like Earth and decide which ones deserve a closer look. TESS is scheduled to launch on top of a SpaceX Falcon 9 rocket at 6:51 tonight, Eastern Time, from Space Launch Complex 40 on Cape Canaveral Air Force Station. TESS has a window of 30 seconds to launch and will take 2 months to reach orbit. Coming up, we'll hear from SpaceX at its Mission Control Center in California. We'll also share more about the thrilling discoveries TESS could uncover. But first, we are now about 20 minutes from launch, so let's check in with NASA's Josh Finch and Mike Curie in Kennedy's Mission Director Center for a weather update. Guys?
Thank you, Marie. I'm Josh Finch.
And I'm Mike Curie, and we are in the Mission Director Center in Hangar AE on Cape Canaveral Air Force Station, very close to Space Launch Complex 40, where the Falcon 9 rocket is poised for launch today. We have teams from SpaceX, NASA, and the U.S. Air Force working from the east coast of Florida to the west coast of California to launch NASA's planet-hunting spacecraft. Our first launch attempt on April 16th was scrubbed to allow launch teams to further review data for the SpaceX Falcon 9's guidance, navigation, and control system. And that analysis is now complete, and we are go for today's launch at 6:51 and 31 seconds p.m. Eastern Time.
Marie, you asked about the weather for today's launch, and the forecast has improved as well from our first attempt. Today, the skies are clear, as you can see on your screen. The temperature is about 72 degrees, with light winds out of the southeast at about 10 to 15 miles per hour. We have no primary concerns for launch today. Our probability of violation is less than 10%, meaning we're over 90% go for today's launch in terms of weather.
The U.S. Air Force is also monitoring the eastern range to make sure commercial and personal aircraft are clear of the restricted area and that waters within the launch safety zone are clear of any boats. We also received a collision avoidance update, which is tracking any potential objects in space. It's all clear for today. We have no so-called COLAs, so we're on time for the opening of the launch window.
Teams continue to work through the necessary procedures to prepare the Falcon 9 rocket and the TESS spacecraft for launch, including loading fuel into both rocket stages and making sure all systems are properly checking out. As Mike mentioned, we've done collision avoidance with the Eastern Range, a checkout of the Autonomous Flight Termination System, and the loading of RP-1 fuel, our rocket-grade kerosene, began at about T-minus 1 hour, 10 minutes. The Eastern Range confirms that it is go for launch of the Falcon 9 and the landing of the first stage, and liquid oxygen began being fueled at T-minus 35 minutes. So with weather a go and things tracking on time here, Marie, will go back to you.
All right, thanks, guys. This is not the first time NASA has explored the possibility of other Earths orbiting distant stars. The missions of Kepler and K2 have found thousands of known and likely planets that forever changed our understanding of what lies beyond our solar system. TESS, a joint mission between NASA and the Massachusetts Institute of Technology, will continue this groundbreaking work. But TESS is different from Kepler in 2 important ways. First, TESS will cover an area of sky 350 times larger than Kepler. TESS will also look at stars up to 100 times brighter than those Kepler studied. This will show us planets closer to our solar system, making follow-up observations much easier. Using TESS data, missions like the James Webb Space Telescope can hone in on specific traits of these planets. Are they water worlds or perhaps big rocks like Earth? And could they support life? Scientists expect to find about 300 planets the same size as Earth or up to 2 times larger. TESS will be the first launch of its kind for SpaceX, and NASA is proud to be expanding our range of missions with our commercial partner. SpaceX's Brian Malstedt joins us live from their Mission Control Center in Hawthorne, California with more. Brian?
Hey everybody, my name is Brian Malstedt and I'm a software engineer here at the SpaceX headquarters in Hawthorne, California. Now, it is not every day that you can say you're launching a planet hunter, so today we're all very excited to launch such a cool spacecraft. Now, most of you have probably watched our launches to the International Space Station, or the ISS, but the profile of today's mission is quite a bit different. For our resupply missions to the ISS, Falcon 9 delivers Dragon to a low Earth orbit at around T plus 14 minutes, and then Dragon makes its way to the ISS about a day and a half later. Now, for today's mission, Falcon 9 will be delivering TESS to an elliptical Earth orbit, from which TESS will then move on its own power to its final lunar transfer orbit. Now, that mission profile just described is much like more of our geosynchronous transfer orbit missions or our GTO missions. Now, after separating from the first stage, the second stage will coast for about half an hour with the deployment of the TESS spacecraft at about T plus 49 minutes. Today, TESS is flying on a new Falcon 9 rocket, but we are planning to land and recover the first stage booster after today's launch so that it can be reflown on a future SpaceX mission. Now, for this mission, we will be attempting to land on our autonomous spaceport drone ship, affectionately named, of course, I Still Love You, and we do hope that the signal holds out long enough so that we can bring you live video of that landing attempt. Now, the drone ship is currently stationed out in the Atlantic Ocean waiting to welcome the first stage back to Earth about 8 minutes after liftoff. And remember, landing the first stage is the secondary objective for today's mission. Our primary objective is to deliver TESS to orbit, and so far things are looking great for an on-time liftoff at 6:51 p.m. Eastern Time. Back to you, Marie.
Fantastic. Thanks, Brian. TESS is decked out with impressive equipment to carry out its mission. 4 spinning wheels allow TESS to turn and point at specific stars. 4 state-of-the-art cameras will look for changes in light that indicate a moving planet. Each camera has 7 stacked lenses to bring images into focus. A shade protects the cameras from the sun's heat. A computer inside TESS stores data, and an antenna transmits that data back to Earth once every 2 weeks. Now, interpreting the data is just as important as gathering it. NASA's Amanda Griffin is live at Kennedy's Turn Basin with TESS program scientist Dr. Martin Still with more. Amanda?
Thanks, Marie. Dr. Still, thanks so much for joining us here today. Can you tell us a little bit more about these exoplanets that we're hunting?
Sure. Our solar system has 8 major planets, including the Earth, of course, and they all orbit our sun. If we look at stars elsewhere in the galaxy, they also have orbiting planets, and we term those exoplanets.
And so how is TESS helping us study those exoplanets?
If you can remember, the Kepler mission is still operating, and its task was to determine how common planets were in the galaxy. And the answer is they're everywhere. They're all over the place. So that allows us to build and launch TESS and do a survey for the nearest planets around the nearest stars. Now, Kepler, because of the nature of its survey, while we're all excited about the planets and the planetary systems that it found, you'll notice that there was not so much, there's not so much of the story after the original detection, because those planets are so far away, we could not follow up and do more science. With TESS, these stars and planets are so much closer that we can then characterize, we can find atmospheres around these planets, characterize the constituents of those atmospheres, so we'll be able to do follow-up, and so the stories of these planets will continue on long after detection.
And so why do we care about these exoplanets?
Because it's our human nature to understand what the universe is. It's our human nature to understand where we came from, where we are going, and of course, are we...
The first stage, which is the bottom two-thirds of the rocket, is our booster stage. And that, along with the 9 Merlin engines, is what does the bulk of the work to get Falcon 9 from the ground and up into the thinner parts of the Earth's atmosphere to the edge of space. And we're going to attempt to land this stage today on the drone ship after it separates from the upper stage. Now that upper stage, or stage 2 as we call it, that's right on top of stage 1 and has a single MVAC engine on it. That's Merlin vacuum engine. That's the engine that ignites after stage 1 separates and begins its journey back to Earth. The second stage is what's going to carry TESS from the edge of space and accelerated it to orbital speeds of just over 7.5 kilometers per second. Now TESS is currently sitting on the very top of that stack inside of our 17-foot diameter payload fairing. That's that nose cone structure you see on your screen up top. The fairing is what protects the spacecraft from aerothermal heating and loads as we launch it into space. Once we reach vacuum, we're going to separate the two halves of that nose cone of that fairing and have them come back to Earth because we don't need them anymore. Now the truss structure that you see on your screen there, that is referred to as our transporter erector. This is what we use not only to roll the rocket out of the hangar and to the pad and then to lift it up and support it in its vertical position, but is also what routes Falcon 9's fluids, power, and telemetry umbilicals from the ground systems all the way to the vehicle itself, and does so until Falcon 9 goes on internal power and launches and clears the pad. At that point, the vehicle's internal flight computer and automation and radio frequency communication is what's going to take over. Now, following successful deployment of the TESS spacecraft, this is going to be the 52nd Falcon 9 launch, the 24th Falcon 9 landing if we're successful today, and SpaceX's 8th launch this year. Operators began loading propellant on the Falcon 9 at T-minus 70 minutes. And Falcon 9 is powered by bipropellant engines. That is, they consume a fuel, which is RP1, and an oxidizer, which is liquid oxygen. Fuel is about 90% or so loaded on the rocket in on stage 1, and 75% loaded on stage 2. Oh, I'm sorry. Actually, RP1, the fuel, is fully loaded on stage 1 and 2. And it's LOX that's about 90% loaded on stage 1 and 75% loaded on stage 2. Now, liquid oxygen is that super chilled oxidizer that we use inside of our ox tank. And coming up next, what we're going to hear on the call out is engine chill. This is where we flow a small amount of that liquid oxygen through to the engines in order to cool them down to their operating temperature, so that when we start feeding them their full flow of liquid oxygen in flight, that LOX stays nice and cold and doesn't heat up and start to boil off and cause bubbles and other performance issues on the engines. Listening in on the weather nets, it's sounding like we are looking good for an on-time launch today. I'm not hearing about any issues with upper-level clouds. Our ground-level winds are looking within limits, as are those upper-level winds, and we're within our lightning rules. Spacecraft is currently healthy, it's on internal power, and the range is currently go for an on-time launch today. So today's mission is really, really cool. We are launching NASA's Transiting Exoplanet Survey Satellite, or TESS. This is a mission that's operated by MIT, managed by NASA's Goddard Space Flight Center, and it's the second launch that SpaceX has conducted for NASA's Launch Services Program. And at just 365 kilograms and just under 5 feet tall, TESS may be small, but it is doing big things. This Planet Hunter is an orbital observatory that will discover thousands of planets by monitoring over 200,000 stars in nearby planet systems, or star systems. Its science instrument is comprised of 4 high-tech, wide field of view cameras designed and manufactured by MIT's Lincoln Laboratory. These cameras will allow TESS to detect exoplanets, which are planets that are outside of our solar system. It does this by looking for a phenomenon known as a transit. This is where a planet passes in front of its host star, causing a periodic dip in that star's brightness. This allows scientists to assess the size, mass, atmospheric composition, and structure of those planets. And this is particularly exciting to astrophysicists and astrobiologists because some of those planets may fall into what is referred to as the habitable zone. That means it might have the right conditions to sustain liquid water and potentially support life. Falcon 9 will be injecting TESS into an elliptical high Earth orbit that at its highest point reaches 273,000 kilometers. That's over 2/3 of the way to our moon. After TESS separates from Falcon 9 over the next 60 days, the spacecraft will use its onboard thrusters to perform a series of maneuvers, which includes a flyby of the moon in order to slingshot it into its final high Earth science orbit. This orbit is what's going to give TESS an unobstructed view of the night sky, allowing the spacecraft to observe and catalog thousands of exoplanets for future studies by the James Webb Space Telescope, the Hubble Space Telescope, and large ground-based observatories.
Internal sequences have started.
All right, we are about 4 minutes and 45 seconds away from liftoff. So let's check in on the rocket one more time before stepping into the terminal count. Fuel is fully loaded on both stages, and liquid oxygen is being topped off right now as we speak. The rocket is also now pressurizing itself with helium gas. We use that gas in order to maintain the structural strength of the rocket while on the ground and in flight. And very soon what you're going to see is those cradle arms that are holding the rocket. They're going to open up, and the transporter erector is going to lean back slightly. It's going to retract. You also might see some venting coming from the side of the TE. That's totally normal. It's just liquid oxygen that's boiling off, heating up, and being released from the tanks. At T-minus 1 minute, the rocket's internal flight computers are going to take over, which you'll hear on the countdown net as Falcon 9 is in startup. The range is currently looking good for an on-time launch today. The payload is healthy on internal power and is go, and weather is go. We are looking awesome for a 6:51 p.m. T0. Now, our launch window today is only 30 seconds long, but that's pretty much an instantaneous window. If for some reason we can't get off today, we'll come back again tomorrow at 7:09 p.m. Eastern Time to give it another go. So with that, let's listen in to the last 3.5 minutes of terminal count.
Strike is at retract angle 88.3 degrees.
Go bleed verification. Stage 1 lock cell complete. Stage 2 dump manifold secured. Stage 2 lock cell complete. Falcon 9 is on internal power. Vehicles and self-line.
Ground gas closeouts is starting.
AFTS is ready for launch. Falcon 9's in startup.
Ground gas closeout is complete.
Stage 2 pressing for flight.
LD, go for launch.
Stage 1 is at startup pressures.
T-minus 15 seconds.
Falcon 9 is configured for flight.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Liftoff.
Ground operators proceed to section 575. Flight report to procedure 3070 post-launch flight operations.
Vehicles pitching downrange. Stage 1 propulsion is nominal.
As you just saw, Falcon 9 has successfully cleared the pad and is now on its ascent with the TESS spacecraft in its fairing. Now coming up in about 15 minutes, you're going to hear the call out that Falcon 9 will have hit max Q. That stands for maximum aerodynamic pressure. That is the point at which the rocket is seeing its highest stresses on its ascent.
Vehicle has passed maximum aerodynamic pressure.
You can tell by the cheers and what you heard on that call out, we have gotten through max Q. Coming up next, you're going to hear the call for MVAC
MVAC engine chill has begun.
And that was it. That is where we chill in that Merlin vacuum engine down to operating temperature. Now coming up here shortly, you're going to hear 3 big events happening in rapid succession. The first is MECO, that stands for main engine cutoff. That is where all 9 of the first stage engines are going to shut down. That's in preparation for the next step, which is stage sep, or stage separation. That is where stage 1 will separate from stage 2. Stage 1 will make its way back down to the drone ship. Stage 2 will continue on with TESS to its orbit. And then you're going to hear second engine start. That is the ignition of the second stage engine. Let's check it out here.
MECO.
Stage separation confirmed.
Stage 1 is under its foot. MVAC ignition.
All right, and as you just saw, we had a successful stage separation and a successful ignition of that second stage engine. Now the fairing should be deploying at any moment. There we go. And you can see that tiny but strong TESS spacecraft inside of that, or on top of stage 2. Now stage 1 is making its way back down to Earth. What we're going to see coming up pretty shortly is a boost back burn.
Grid fin deployed.
Grid fins have deployed.
Both stages following nominal trajectories.
Acquisition of signal, Bermuda.
Right now, stage 2 is going to continue to burn until T+8 minutes and 20 seconds, while stage 1 makes its way back down to Earth. Now, there are 2 more burns coming up for stage 1. The next one's going to be the entry burn. That's where we're going to reignite 3 of the stage 1 engines. And that burn is intended to slow down stage 1's descent as it makes its way through that thick upper atmosphere. We'll be seeing that at 6 minutes and 29 seconds or so in about 2 minutes. We're hearing that stage 2's burn is still performing nominally. Okay, stage 2 is going to continue to burn for about another 3 minutes and 1 minute until we see that re-entry burn. Now, after that re-entry burn, stage 1 is going to continue on making its way down to the drone ship, and coming up thereafter will be the landing burn. That'll be the 3rd of the 3 burns, and at that point we're going to reignite that center engine, E9, and that'll bring us down to 0 velocity, hopefully standing up tall on the drone ship. Continue to hear that impact D is looking good. Turbopump performance is good. Everything is performing nominally on stage 2, which is great news.
Stage 2 continues to follow a nominal.
As you can see, that burn has begun, that entry burn. This burn is going to go for about another 10 seconds or so before it shuts down. And the entry burn is complete.
Stage 1 entry burn shut down.
Okay, as stage 2 continues to burn, we are getting TESS into a nice circular orbit where TESS will then, well, stage 2 with TESS on top will coast for about 35 minutes.
Stage 1 is transonic.
As you heard, stage 1 is transonic. We're about 10 seconds away from that landing burn. Note that the drone ship is situated approximately 300 kilometers off the coast of Florida, and as you can see, that landing burn has started. Let's see if we can catch it. Has successfully landed on A Course I Still Love You. This marks the 24th successful landing of a Falcon 9 first stage. And meanwhile, we've reached SECO, which is second engine cutoff. Stage 2 has shut down its first burn. Now, stage 2 should be in a parking orbit of about 250 by 250 kilometers. Stage 2 is now going to coast for 35 minutes or so. So why don't you come back here at T plus 39 minutes, where we're going to bring you back to the webcast, where we're going to resume it, and we will be relighting the second stage engine for a second time in order to raise the apogee of our orbit to 273,000 kilometers. That gets us into TESS's highly elliptical orbit, where we will then deploy the spacecraft. So we're going to continue showing you some live views of space and of TESS and of stage 2. And we'll be back to commentate the webcast at T plus 42 minutes.
Also signal Cape Canaveral as expected.
near and bright stars to ourselves, and so this is stars within the range of 30 to 300 light years or so, whereas Kepler looked at stars that were in the range of 300 to 3,000 light years.
And is there anything else interesting? I think you were talking about the lenses maybe and things like that that are really unique for these cameras.
Yeah, so the TESS lenses look and the wavelength
So can you use these cameras here on Earth?
Yeah, so actually in the lab when we were testing the cameras for the first time and we received a prototype, we had it in its test chamber and we blocked the window for the chamber and left just a little pinhole for light to come in, and we were able to have people stand in front of the cameras and take a selfie.
Oh, that's probably the best selfie ever. And I think we also have a shot. You guys went on a roof at MIT?
Yes, so TESS, we took one of the prototype cameras again in a test chamber that simulates the conditions of space, and it's a cold vacuum, and took it up onto the roof of a building at MIT. And MIT in Cambridge has a lot of light pollution, but we were still able to take an image of this field that had all of these stars, and it was this beautiful dense image of all of these beautiful stars, and the images are only going to get better now that we're heading to our orbit.
Right, and I can't wait to see them. So congrats on launch today, and
thank you.
Good luck.
Thank you.
Back to you, Marie.
Thanks, Amanda. TESS will track down exoplanets ranging from Earth-sized to gas giants, orbiting a wide range of stars with different orbital distances. NASA Edge's Blair Allen sat down with TESS project manager Jeff Velosin to understand how to detect planets that are light years away. Blair?
We're here at NASA Goddard Space Flight Center with Jeff Velosin, the project manager for TESS, the Transiting Exoplanet Survey Satellite. Jeff, this is a very exciting mission looking at exoplanets. Tell us, what is the TESS mission?
So it's another mission in NASA's effort to learn more about planets outside our solar system. So it's kind of a, an evolution, right? When I went to college, there was no such thing as an exoplanet. One had never been found. Nobody thought there'd ever be one found because they're so small compared to the stars that they go around. So when the Kepler mission flew, maybe 10 or 15 years ago, all of a sudden, thousands of exoplanets were discovered, that there were these orbiting planets around stars outside the solar system, that some of them were as small as the Earth even. So Kepler was able to find planets, mostly larger ones, and they focused on one area of the sky. So for years, they just looked at one area. So we knew that there's now lots of planets, and probably everywhere you look, there are lots of planets. So our mission is a survey mission. So the TESS has a survey word in it. And survey is all about, we want to look through the whole sky. So we're not going to just look in one spot. We're going to look all around the sky over a 2-year period and look for planets. We have very sensitive cameras. We're going to look for Earth-like planets that are closer to Earth.
Right.
Now, by being closer to Earth, it allows further follow-up study. Because if you could find planets orbiting stars that aren't that far away, now the James Webb Telescope, with its big, powerful mirror, can say, okay, I know TESS has told me there's a small Earth-like planet around that nearby star. I'm going to go ahead and focus my powerful telescope. And what happens now is when the planet goes in front of the star, you can actually see the light going through the atmosphere, coming to Earth, and then the spectrum of that atmosphere is available. And the spectrum being what parts of the starlight were absorbed by the planet's atmosphere. And that'll tell you, is there carbon dioxide in the atmosphere? Is there oxygen in the atmosphere? So all of a sudden you can learn about an Earth-like planet and what atmosphere it has. So
is TESS then really sort of putting out this map of potential planets for James Webb?
Yeah, exactly. So that's where we fit in, right? So Kepler proved that you could find stars almost anywhere you look that have planets around them. Kepler showed that there's a variety of different types of solar systems that we never would have imagined, and that there are Earth-like planets out there. Now with a very sensitive set of cameras on TESS, we have 4 cameras on the spacecraft that'll look out at a wider swath of the sky, and then every month or two we'll move and look at a different part of the sky. But one thing we're going to focus on is looking straight up. Think of it as a north ecliptic pole, and that's a place where the James Webb Telescope can stare at that spot with the sunlight not getting in the way of the observation. So that's a place they would like to look for exoplanets, because if you're going to look at the atmosphere of one of these exoplanets, you have to stare for quite a long time every time the planet goes in front of the star. So it's great if they have these objects available straight up in the north ecliptic pole or straight down. So that's a lot of our focus. And so the goal is to find them candidates to look at.
And it seems like this is vastly different from Kepler in that it is doing this complete, I don't know, 360 full range. I don't know how to describe it.
Right, yeah, a whole sky survey.
Yeah.
And the great thing about that is, imagine what Kepler was able to find just blew everybody's minds. Planets that might be all diamond, planets that might have totally water surfaces. Imagine what we'll find when we now look all over the place. Kepler looked at one little area and found all that. We can't even begin to think about what are we going to find in the survey over a couple of years. So yeah, that's the exciting part about it. And the other thing is, what we'll find out is how big these planets are. So when you see the light being blocked, all you can tell is the size of the planet compared to the star. You can't tell how heavy it is. And if you can't tell how heavy it is, you really can't tell what it's made of. So what we're going to do is ground telescopes can actually look at those same targets. They look at the planet's effect on the star. So you think about TESS as looking at light being blocked. Well, what the ground telescopes are doing is the star is wiggling a little bit as it's spinning around because the planets are tugging on it. The heavier the planet, the more it tugs on the star. That wiggle is really small, but those ground telescopes can quantify the wiggle and then tell you how heavy the planet had to be. Wow. So now you have the size of the planet and the heaviness of the planet, and you can get the density and figure out, is it water, is it solid, is it gas?
Earth-like would be fantastic, but if we find, say, a desert planet, is there, what is the likelihood that we can just go ahead, name it Tatooine, and be good to go?
Yeah, there's a lot of people who are looking for, name your favorite sci-fi movie, right? A lot of people are looking for their favorite sci-fi movie planet, but I think we're going to find that there's probably even more diversity than sci-fi writers have ever thought up. And I think that's already what we've seen from Kepler, is that there's some really weird planets out there. So I think that's what we're looking forward to.
TESS will look specifically for planets with the right makeup to support life. NASA's Stephanie Martin has more on how scientists will use the TESS data.
I'm here with Paul Hertz, Director of NASA's Astrophysics. Now, Paul, can you tell me a little bit about NASA's search for life in the universe and how it's evolved over time?
Well, the first exoplanets, planets around other stars, were discovered with telescopes on the ground. But it took NASA's Kepler Space Telescope to show that almost all the stars in our galaxies are likely to have families of planets around them. And with the Hubble and Spitzer telescopes, we were able to start sampling their atmospheres and learning something about what they're made of. With the TESS satellite, we'll be able to find planets around the nearest stars to the sun.
That's fascinating. Now, why are we searching for life?
Well, humanity has always wanted to know whether we're alone in the universe. With TESS and the other NASA space telescopes, we can find nearby exoplanets and then study them with large space telescopes like Hubble and the James Webb, look for signs of habitability on those planets or even signs of life in their atmospheres.
Now, you mentioned habitability, and I've heard the term habitable zone. What is a habitable zone, and does that mean that there's no chance that life would exist outside of that habitable zone?
Well, we know that in our own solar system, the Earth is very conducive to life. It's a rocky planet, and it's a very balmy temperature where liquid water can exist. Planets like Mercury are too hot. Planets like Jupiter are both big and gaseous and too cold. So we want to find planets which are rocky and are in the Goldilocks zone of their star. We call those habitable planets. We're looking for those because on those planets, we know that life as we know it could exist.
Now, what's next after TESS? What are the next steps to find life?
Well, NASA's next large space telescope will be the James Webb Space Telescope. We'll be launching that in 2020, and it'll be able to study some of the planets discovered by TESS and look for the gases in their atmospheres. Will they have gases like carbon dioxide, methane, oxygen, or water vapor? Gases that on Earth are indicators of life. And after that, we're going to launch the Wide Field Infrared Survey Telescope. It'll have a special instrument on it, a coronagraph, which will be able to let us measure the light directly from a planet without being obscured by the light from the star. That'll let us take the next step in exoplanet studies.
Now, what drives you personally to study these exoplanets?
Well, I think we're all interested in knowing as much as we can about the universe, and whether we're alone in the universe has always been an interesting question. It's really fortunate that today we're at the beginning of that journey. We've only known there were planets around other stars for 25 years, and now we're putting in space the kinds of telescopes that can let us study them in detail. I think that the exciting thing about the TESS mission is after TESS has discovered planets around the brightest stars, you'll be able to go out in your backyard and point to a star in the sky and say, I know there's a planet around that star. I wonder if there's life on it.
That's pretty spectacular. Thank you so much for your time, and we'll go back to you in the studio.
TESS's main goal is to find small planets with bright host stars in our solar neighborhood. This will open the door for scientists to perform detailed investigations of the planets and of their atmospheres. NASA Edge's Chris Gersh met with Stephen Reinhardt of NASA's Goddard Space Flight Center to learn more about the science behind spotting potential Earth-sized planets.
We're here with Stephen Reinhardt, the project scientist for TESS. How you doing, Stephen?
Not too bad.
What's TESS all about?
Well, TESS stands for the Transiting Exoplanet Survey Satellite.
Okay.
And it's NASA's next Explorer mission, being led out of MIT. And it's designed to actually search all of the bright nearby stars, or nearly all of them, looking for signs of planets, exoplanets. In fact, what it's looking for are transits. It's looking for those events where a planet passes in front of its host star, blocking part of the light, and that gives us this little change in the brightness of the star that tells us that a planet is there.
How are you able to detect that transit from millions and millions of miles away? Because when we've seen the Venus transit, when you see that pretty up close with binoculars, you can see it even live, but how can you see something millions of miles away?
Right, well, the Venus transit is a perfect example. Okay. When you watch that, and if you watch a video from some of the other NASA missions, you can see this black spot passing across the face of the sun. Well, now imagine that the sun were just farther away. You don't see the spot anymore. You can't resolve it with binoculars or a telescope or anything else we've got right now. But what you can do is you can see that star gets so very little fainter. For instance, if you have Jupiter passing in front of our sun, you see about 1% of the light from the star gets blocked by Jupiter. Okay. So if you were watching that star very carefully and were very, very far away, you would see that the light just suddenly drops and then comes back again. Okay. And so that's the signal we're looking for. We're looking for that little drop in brightness, and we're looking for it to happen regularly, right? If you, for instance, have Earth around the sun, once every year, it would pass in front of the star and block that light. So you're looking for this repeated small change in the small dip in the brightness of the star.
So given that, looking at the brightness, I mean, you have to have pretty sensitive cameras to be able to detect that dip.
That's right. So, you know, I said Jupiter's 1%. Earth around the sun is 1/100th of 1%, or 100 parts per million.
Wow.
So what TESS is designed to do, those cameras are designed to be exquisitely sensitive so that we can detect things that are small changes less than 100 parts per million. And really the thing that dominates a lot of the uncertainty are the stars themselves. Stars are not quiet at the tens parts per million level. So you've got this stellar noise, and then you've got the sensitivity of the cameras, but together we should be able to detect small Earth-sized planets around stars like the sun and even smaller than the sun.
Now I understand you're going to be looking at something like 200,000 stars in that 2-year mission. Are you picking out those stars? Or are you just kind of going to a region and say, look, we're just going to look for opportunities in a certain region?
So it's a predetermined list, except where it's not. Most of this list is, there's a group of the science team that have worked on a thing called the TIC, the TESS Input Catalog. Okay. And the TIC has about 3 billion stars, if I remember my numbers correctly, in it. Obviously, we're not going to be looking at all those. Right. It's every bright object in the sky down to a certain brightness level. It's huge. But then there's the actual target list. And that's between 100 and 200,000 stars. And these are stars that are specially selected for specific observations with TESS using a 2-minute cadence. So every 2 minutes, they measure the brightness of that star. Okay. And those are the stars that have the highest likelihood that we'll actually be able to find an Earth-sized planet around them. So stars that are smaller, it's easier to find smaller planets around smaller stars. Stars that are brighter, and so on. In addition to that, there are additional stars that are proposed by members of the general community through the guest investigator program, and that means that we can observe some other stars that were not necessarily viewed as great targets by the science team, but which somebody out in the community says there's a good reason to look at this star, so we will. And in addition to that, we have the full frame images. So every 30 minutes, TESS takes a picture of the entire field of view, which is 24 by 96 degrees.
Wow.
It's huge. And with that, we're going to be able to find a lot more planets. Now, most of those planets are going to be the large planets. They're going to be Jupiter-sized planets and so on. But it's, about 10 times as many of those in the full frame images than the number of planets that we'll find in those postage stamp data, which are really focused on trying to find the smaller planets.
Now, look at our solar system. Our sun is an average star. Are you kind of targeting those type of stars for possible Earth-like planets, or could you have stars that are much bigger than our sun that could potentially have an Earth-like planet?
So, first off, let me say that when we say that our sun is average, we are really wrong. Our sun is actually kind of unusual. It is a sort of average in size, but it's not actually very active compared to most stars.
Oh, wow.
And there's a lot of other stars out there that are very, very different. So a lot of the stars that TESS will observe are what we call the M dwarfs. So these are much smaller than the sun. Okay. They're much cooler than the sun. So for instance, the habitable zone, that region around the star where you could have liquid water on the surface of a planet, is much, much smaller than you have around the sun. Those are going to be very good targets for TESS because they're smaller. Okay. The larger stars, if you start talking about some of the stars that are a few times bigger than the sun, the problem is that now trying to find a small planet around this big star, it gets really hard. So, imagine that you have a star that's 3 times bigger than the sun, but you have that same planet, then suddenly it's 1/10 of the as easy to detect as it was before. So while we will look at some of those, it's going to be really hard to find the smaller planets around those kinds of stars. But those are important observations to make because we haven't done a lot of observations of those larger stars looking for exoplanets yet because they're hard. And so we really don't know what the population of planets looks like around those kinds of stars.
Final testing of the TESS spacecraft was done right here at Kennedy Space Center. That happened in the Payload Hazardous Servicing Facility. NASA Edge's Franklin Fitzgerald had a chance to see the spacecraft in the clean room and talk with Orbital ATK's Robert Lockwood.
Hey, today I'm hanging out with Robert Lockwood, who is the spacecraft program manager from Orbital ATK for TESS.
Hey, Franklin.
Hey, man, we are going to go over to this big building. Is this a high bay or a clean room?
Yeah, it is. It's a big high bay clean room. It's the Payload Hazardous Servicing Facility.
Once I get in there, I'm going to do a little bit of a B-roll for our show, but also we'll have an opportunity to do an interview.
Okay.
Do I have to put on a bunny suit?
Yeah, you do. You're going to get all covered up. The main source of contamination for spacecraft is people. So we're going to cover you all up in a bunny suit, going to put a mask over your face, but you'll still look pretty.
Oh, I'm glad I saved lunch for after the interview. So Robert, we're here in this high bay clean room. What types of tests or checkouts are done for tests in this facility?
Well, primarily in this facility is for propellant fueling. We're going to fuel the vehicle with 45 kilograms of hydrazine to perform our on-orbit maneuvers. This facility is certified for propellant fueling, so that's primarily why we're in here. We also have other performance tests that we do. Check it out after it went from Dulles to here, make sure everything worked after shipment, deploy the solar arrays and stow them. We also do a number of checkouts and closeouts. One of the things they're doing today is putting the vehicle on a high stand so that we have easier access under the vehicle to close out some of the parts on the bottom part of the vehicle. When our partners from SpaceX arrive here with the fairing, we will attach the vehicle to the fairing, encapsulate it, and then they will transport it over to Space Launch Complex 40 for launch.
As the program manager for TESS, tell me about some of your duties.
Primary among those are moving all the little parts around, the logistics for keeping things on schedule, keeping staff working in the areas they need to, interacting with all of our partners at MIT, at Goddard Space Flight Center, to make sure that things just keep moving smoothly towards launch.
See, when you talk about partners, you've received components for tests from all over the country, but when you talk about MIT, they are responsible for pretty much the major part of the satellite, the cameras, is that right?
That's right. So we have one instrument. It's comprised of 4 wide field of view CCD cameras. Those are manufactured at MIT Lincoln Laboratory and then delivered to us for integration.
And integration was done at Orbital in Dulles, Virginia, right?
That's right. We have a full facility there for integrating all the parts and testing it.
Talk to me a little bit about the testing. I know that there is environmental testing done for all satellites. Can you tell us a little bit about the process that TESS went through at Orbital?
Sure. We received the 4 cameras sitting on its camera plate and integrated it to the top of our spacecraft bus to form a full observatory. Then we take it through a set of comprehensive functional tests just to make sure that everything is working correctly. We then put it on a shaker table or vibration facility where we shake it at levels that simulate launch environments. We put it in a chamber to test it for electromagnetic compatibility. Then we put it in a thermal vacuum chamber to expose it to the highs and lows, hots and colds of on-orbit environments.
Robert, did you encounter any obstacles along the way managing this program?
None to really call out. It's the typical thing when you put spacecraft together in a facility like Dulles, Virginia. There are a number of spacecraft processing through there. So it's a continual shell game when your part is ready to go integrate or when your part's ready to go onto the vibe table for test or into the TVAC chamber. But no obstacles that really stopped us from getting here on time, and in fact we've got about 3 weeks of margin to sit around now, so we're actually even a little early.
Yeah, well, yes, when I was in here shooting some B-roll, TESS was uncovered, but now it's bagged, so I'm assuming you're pretty much on the back end of everything you need to do.
We are. We're bagging it to keep her safe for about 3 weeks while I let my staff go back to Virginia and see their family, and we'll keep one person down here just periodically checking on her, but she's just going to sit there and wait. But then we will come back in 3 weeks' time, take the bag off, and continue on processing.
TESS is almost ready to open its solar arrays, or wings, to power the spacecraft. Let's go back to Josh and Mike to take us through the deployment. Guys?
Hey, Marie, thank you. We actually are about 3.5 minutes away now from the second stage engine burn number 2, which is a burn that'll last a little less than a minute, Josh. And when it ends, it will place TESS in the right position for deploy into space. And that just is the beginning of the journey. We'll have more information, and we'll be back to fill you in on when the burn takes place.
The launch happened on time today at 6:51:30. It was a beautiful launch. Weather cooperated with us today. No chance of precipitation, no clouds in the sky. It was really a beautiful launch.
Absolutely.
TESS will search the sky for telltale signs of exoplanets or planets looking for other stars. TESS will survey nearly the entire sky, and we have a video to tell you more about that.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. Led by MIT, TESS will find thousands of new planets orbiting nearby stars. During its 2-year survey, TESS will watch a wide variety of stars, looking for signs of planets ranging from Earth-size to larger than Jupiter. Each of TESS's cameras has a 16.8 megapixel sensor covering a square 24 degrees wide, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a long strip of the sky called an observation sector. TESS will watch each observation sector for about 27 days before rotating to the next. It will cover the southern sky in its first year, and then begin scanning the north. TESS will study 85% of the sky, an area 350 times greater than what NASA's Kepler mission first observed, making TESS the first exoplanet mission to survey nearly the entire sky. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the 2 missions to work together to first find and then carefully study exoplanets, expanding our understanding of worlds beyond our own.
Okay, we are a little bit more than a minute away from the expected restart of the SpaceX Falcon 9 second stage Merlin engine. This burn, once again, will last under a minute. It will place the TESS spacecraft in the proper location to be deployed into space to begin its journey. Looking live now at the second stage engine, at the Merlin engine. We're expecting the burn to begin in about 30 seconds. Second stage, along with the TESS spacecraft transiting across the globe, having passed out over Africa. Liquid oxygen tank being pressurized for the burn.
35-minute coast, and the second engine is about to reignite. Just heard on the nets that MVAC chilling has begun, and pretty soon the second stage will be reigniting to take TESS to its deployment orbit.
Fuel tank coming up to pressure for the burn.
30 seconds, we're going to see that engine reignite. From there, the burn is going to last for about 1 minute before the engine shuts down again. And a few minutes after that, the TESS spacecraft will deploy. As you just saw there, we have reignited the second stage. And this burn's going to last for about a minute. This is raising the apogee of our orbit so that we can drop TESS off at a place where it can then properly begin to perform its own orbit raising maneuvers to get it to that point where it can perform its lunar flyby. We are beginning to throttle everything down. I'm hearing that everything is looking totally normal on this burn, which is really good news. And the engine has shut down.
Have that cut off.
So for about 5 minutes, the stage is going to coast with TESS on top, at which point the payload is going to deploy. Now, the way that that works is there is what is referred to as a payload adapter that is sitting on the top of our second stage, and TESS is attached to that. It's attached via a clamp band, which is basically like a banded spring. We'll send a separation signal to Falcon 9, which will then open up that clamp band, and there will be 4 springs inside of that payload adapter, 4 compression springs that will give TESS a little gentle push to push it away from stage 2. And after a while, a few minutes after that, TESS is going to turn on its transmitters, on its receivers, deploy its solar arrays, and begin its mission. So let's watch these live views for the next 4 minutes or so, and we'll come back for a live view of payload deploy.
and the second stage burn is complete. The second stage continues, as you can see on your screen there. And with now, we will go to a video of Stephanie Martin, who is going to help you learn a little bit more about how we find exoplanets around habitable zones, the Goldilocks zone of stars. We'll go to that video now.
I'm here with Doug Hudgens, the program scientist for exoplanet exploration. Doug, thank you so much for joining me.
Thank you for inviting me.
Now, can you tell me a little bit about why we study exoplanets?
We study exoplanets because we want to understand first just how planets form and evolve, what the whole exoplanet zoo looks like, because our own solar system has the 8 planets that we know of, but in fact finding other solar systems, we find other planets, other types of planets that we maybe don't have in our solar system, but we also find planets that are arranged in different orders with gas giants close to their star and other planets further away, and all of that tells the story of how planetary systems come to be. The TESS mission basically uses the transit technique to detect exoplanets, which means we watch many stars and look for a tiny dip in brightness that occurs each time a planet orbits and passes in front of the star. Now, when TESS detects a exoplanet transit, really that's just where the science begins, because there are also things out in space that can mimic or might fool us into thinking that there's an exoplanet around the star when in fact it's something else entirely. So the first thing that we have to do is we go to ground-based telescopes. Members of the science community, certainly the TESS science team, will be very involved and very active going to ground-based telescopes, carrying out observations of those transiting systems to kind of rule out the astronomical false positives that might trick us.
Now, how can citizen scientists and amateur astronomers help look for these exoplanets?
Well, this is really exciting. The nice thing, the great thing, the exciting thing about TESS is that it is going to be looking at the nearest and brightest stars to the Earth. Now, its predecessor, the Kepler mission, which did a fantastic job in discovering a huge number of planets, most of the stars that it looked at were very faint and largely beyond the grasp of amateur-sized telescopes. TESS is looking at stars that are going to be brighter and much more accessible to ground-based observations and to amateur telescopes. So scientists that have a good quality telescope are going to be able to themselves contribute by carrying out observations of these systems just simply because they're more amenable to their equipment.
Now, how do these amateur astronomers get involved?
In just under a minute here, we'll be seeing the spacecraft separate from Falcon 9. That beautiful image of the Earth behind us there. It's one of the planets TESS is going to look at in its lifetime. And as you can see there, we have had successful separation of the TESS spacecraft. And it's going on its beautiful mission to look at thousands of planets outside of our solar system. And with that brings us to an end of our webcast, as Falcon 9's job is done for today. So this was a pretty successful mission, right? We had a successful Stage 1 ascent and landing. Stage 2 has properly deployed the TESS spacecraft into its intended orbit, and TESS is now on its way, and hopefully we'll hear soon about the health of the payload. I want to give a big thank you to the NASA Launch Services Program for their faith in us, to Goddard Space Flight Center, to MIT, and to the 45th Space Wing for their range support for today's mission. You can follow SpaceX on social media via our Twitter feed as well as our Instagram. You can also check us out on SpaceX.com. And if you want to learn more about the TESS mission, visit nasa.gov. Thank you all so much for joining today, and we'll catch you at the next launch.
So with the successful deploy of the TESS spacecraft, the next major milestone is the beginning of solar array deployment. That activity is expected about 8.5 minutes after spacecraft separation. So in about 7 minutes from now, we'll of course be back to join the beginning of that. That process will take about 20 minutes to complete. We'll rejoin in time for you to track the deploy of the solar arrays from the TESS spacecraft.
TESS will fly in an orbit that completes 2 loops around the Earth every time the Moon orbits once. This special orbit will allow TESS's camera to monitor each patch of sky constantly, for nearly a month at a time. To get this into orbit, TESS will make a series of loops to build momentum. Then, the Moon's gravity will push TESS to its final orbit, 60 days after the launch. Here's another video to tell you how that works.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. Led by MIT, TESS will find thousands of new planets orbiting nearby stars. To accomplish this, TESS will fly in a special highly elliptical orbit that maximizes the amount of sky the spacecraft can image. Once TESS has launched, it will expand its orbit until it can get a gravitational assist from the Moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the Moon's orbital plane. TESS orbits Earth in exactly half the time it takes the Moon to orbit once. This feature helps stabilize the spacecraft's orbit against tugs from the Moon's gravity. TESS will spend most of its 13.7-day orbit observing the sky. As it approaches Earth, TESS will rotate and transmit all its accumulated data to scientists on the ground. Over 2 years, this will allow TESS to study nearly the entire sky and potentially find thousands of new exoplanets.
We're 53 minutes, 41 seconds since the launch of the Falcon 9 rocket carrying the TESS spacecraft. Successful first and second stage burns have placed TESS into its proper location in space. It's been deployed from the Falcon 9 second stage. Solar array deploy is an activity that is expected to take about 20 minutes from the time of spacecraft separation. Here at Hangar AE on Cape Canaveral Air Force Station, TESS controllers are monitoring the spacecraft, reporting on acquisition of telemetry. They'll be looking for power positive indications from the spacecraft. We're expecting the beginning of solar array deploy on the TESS spacecraft in about 2 minutes, 57 minutes, 58 seconds after liftoff.
And we are just under a minute away from the start of the solar array deploy. The spacecraft is now sun-facing.
Acquisition of signal, Auckland.
And we have just received successful deployment of Wing 1 of the solar arrays of the TESS spacecraft. And you can see clapping there from the TESS team, confirmation of the second wing of the solar array has successfully deployed. TESS will spend the next 60 days getting to its proper orbit to do its primary science mission to find exoplanets outside of our solar system.
A very successful day today for NASA and SpaceX. In the beginning of the TESS mission, liftoff of the SpaceX Falcon 9 rocket occurred on time at 6:51 and 30 seconds Eastern Time. The first stage engine did its job, handing off to the second stage engine, which performed 2 successful burns to place the TESS spacecraft in a proper location in space, at which point deploy occurred, followed moments later by the solar array deploys. So at this point, the TESS spacecraft is acquiring power, telemetry is being read, and a lot of happy people at Hangar AE watching the beginnings of a very successful TESS mission, Josh.
Yes, TESS, the Transiting Exoplanet Survey Satellite, is led by the MIT team. TESS will find new planets orbiting nearby stars. To accomplish this, TESS flies in a special highly elliptical orbit that maximizes the amount of sky the spacecraft can image. TESS will expand its orbit until it can get a gravitational assist from the moon. This slingshot will move it into a stable orbit that is tipped about 40 degrees from the moon's orbital plane. TESS orbits in exactly half the time it takes the moon to orbit once. This feature helps stabilize the spacecraft's orbit against the tug from the moon's gravity. TESS will spend most of its 13.7-day orbit observing the sky. As it approaches Earth, TESS will rotate and transmit its accumulated data to scientists on the ground. Over 2 years, this will allow TESS to study nearly the entire sky and potentially find thousands of new exoplanets.
1 hour, 9 minutes after the launch of SpaceX Falcon 9 and the TESS spacecraft, everything has gone so amazingly well, Marie. The rocket launch performed well. The spacecraft has been deployed. Solar arrays are deployed. And with that, we'll turn things back over to you.
Awesome. Great to see that all come together. Thanks, Mike. Let's go now to NASA Edge's Franklin Fitzgerald. He is standing by live with TESS's Deputy Project Manager for Resources. And Franklin, I understand it's a pretty celebratory mood over there.
Yes, it is, Marie. I'm here with Matt Ritzko, who, as you said, is the Deputy Project Manager for Resources for TESS. And Matt, you've been with TESS since it was a stack of papers on a desk. And today you've seen a successful launch. And as Marie said, it was a celebratory, it was applause, there was elation going on in the control room after the solar arrays deployed. Tell us a little bit about how you feel right now.
I'm trying to catch my breath. So thanks, Franklin. I mean, you guys do an awesome job, so thanks for giving us the time today to come and talk. But I just came out of the control room, and we had several rounds of applause. So first we had the launch, and all of us ran outside, and then we came back in, and then we saw the separation, and then we applauded then, and then we had telemetry from the spacecraft, and that instrument team applauded, and then we had spacecraft solar array deployment. So very exciting. It's just the series of things that take place to have a mission enter an orbit and be successful.
Now, the solar array deployment is a major milestone. Tell us about that operation and what it means for the mission.
So it means, from a TESS perspective, TESS is a very simple satellite by NASA standards. There's only one deployment. It's our solar arrays. It's an explorer's mission, which means it's a fast-paced development from soup to nuts, and it's usually lower cost for NASA. So we try to make it as simple as possible. So the only deployment we had on orbit were the solar arrays.
Now, the solar arrays are used for power for the satellite. Now, I assume that it was running off of batteries until the solar arrays deployed. Tell us how they work with the satellite moving forward.
So when we are inside the fairing, the team has batteries that are charged up, and we turn them on, and we put the spacecraft on internal power. Once we launch, the fairing separates, and we have to get the arrays open within a certain period of time, get them pointed to the sun, and then start charging our own batteries again. Without that, if solar arrays don't deploy, you could lose a mission. So for us, it's very important for that process to take place and to turn on all the power on TESS, to start getting all our instruments turned on. So now we're on our own power, and we're flying in space. It can't get any cooler than that.
What are the next moves for TESS moving forward?
So within the next few weeks, TESS is a little more unique. We have 6 burns. TESS has a small thruster on the bottom of it. We'll burn in a highly elliptical orbit. It's a little unique for TESS. And we'll actually do a lunar flyby around May 15th, May 16th. And eventually we'll achieve our final science orbit in June 16th or 17th. And then at that point, we'll be in full-on science operations. So over the course of the next several weeks, TESS is going to be making these maneuvers to get to our orbit. And what makes it so unique is that's how we get the most science from TESS that we possibly can.
Well, Matt, thank you for giving us a little bit of your time this evening. I know that you have to get back to work, but we appreciate you coming in and doing the interview for us.
Absolutely. Thanks for having me today.
All right. Marie, back to you all in the studio.
All right, thanks, Fitzgerald. We want to hear now from the Launch Services Program Manager, Tim Dunn. He's with Josh in the Mission Director Center. Josh, are you there?
I'm here, Marie, and I'm actually here with Tim Dunn as well, the Launch Services Program. Tim, can you tell us about how today's launch went?
Hey, Josh, wow, are we excited? I mean, we just had a perfect countdown and perfect launch of the TESS mission. It was a wonderful day. Obviously, if you got any views outside here off the Central Coast, you saw what a gorgeous day it was. So we had perfect weather for the launch. We had a terrific rocket. The Falcon 9 just continues to demonstrate what a reliable ride it has become. And spacecraft, we turned on TESS spacecraft early this morning, and that went super smooth. We worked one very minor little item with TESS during the countdown. Was really insignificant in the overall picture. TESS was really solid during the rest of the countdown, and the range. Hats off to the United States Air Force and the 45th Space Wing. They continue to have a beautiful range for us to launch on, And again, I don't have a whole lot to talk about as far as troubles during the countdown. It was super smooth, beautiful day, a beautiful launch, a great rocket, and we now have an operational spacecraft on its way to do great science.
And talking about the importance of the TESS mission, can you talk about from the perspective of the Launch Services Program, how it is to launch TESS?
Oh, wow. Well, for us, this was only Launch Services Program's second flight on a Falcon 9 rocket. A couple of years ago, we did the Jason 3 mission from the West Coast, and so this was our second full-up science mission on Falcon 9. So our entire team of engineers and analysts within LSP was able to demonstrate another certification process where we certified this full thrust version, Block 4, that flew today. And to see all of that hard work for the past 2.5 years that the entire Falcon 9 team within LSP put together, to see that rewarded with a successful launch means so much to our team. And it's an incredible team. And SpaceX has an incredible team. Their engineers and analysts here at the launch site here at Cape Canaveral, as well as their team back in California at Hawthorne. My hat's off to them. Terrific launch team. And when you put us all together, the government and the commercial guys together, it's just so satisfying to watch a team kind of seamlessly blend and integrate to accomplish such an important mission for our agency.
So it sounds like a pretty exciting night for both SpaceX and NASA. And the Launch Services Program has a big year, and we've got big stuff coming up still. Can you tell us about what's next for the Launch Services Program?
Absolutely. So we were thrilled to launch tonight, mainly because now it kind of clears a little bit of the runway, because our Atlas V team now has to turn around, get out to the West Coast for the InSight mission, flying in just 2.5 weeks on May 5th from Vandenberg Air Force Base. And then we have a Pegasus mission coming up with the Icon spacecraft, and that's going to stage out of Vandenberg, fly downrange to Quaj, and launch from Quaj in mid-June. Right now we're targeting June 14th. We come back here to the Cape in the end of July. We'll be processing the Parker Solar Probe mission, which is a mission to go study the sun. And it will be the first time LSP has flown a science mission on the Delta IV Heavy. So that's very exciting for our team. And then if all goes according to plan, our 6th and final mission for LSP for 2018 will occur in September from Vandenberg Air Force Base again. And that will be the ISAT-2 mission on the very last Delta II launch vehicle. So I would say if you're a Delta II fan out there, you might want to find your way to the Central California coast right around September 12th, because that's going to be a very special event to watch the final Delta II fly. It's been a workhorse for the agency, and it's really special to a lot of folks that have been in this business for the last 30 years now that it's been flying.
Well, it sounds like we've got a lot to look forward to from the Launch Services Program, and then a lot to look forward to with the TESS mission, which we launched successfully tonight. So with that, we'll sign off and go back to you, Marie. Thank you.
All right. Thanks, Josh. This concludes our live coverage of the successful launch of the Falcon 9 and TESS, the start of a new period of discovery for NASA and the world as we search for more planets and life in space. For more information about the TESS mission, visit nasa.gov/TESS. I'm Marie Lewis. From all of us here at Kennedy Space Center, thank you for joining us. We will leave you now with replays of today's awesome launch. Have a great night.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Radiate from the engine plumes to counter the effect of vibration.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Radiate from the engine plumes to counter the effect of vibration.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. From the engine plumes to counter the effect of vibration.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Status of stage 1.
Stage 1 propulsion nominal. Go.
And we have confirmation.
Stage separation confirmed.
And stage confirmation is confirmed.
You're looking at a live shot of the second stage single.
Stage 1 is energy split. And back ignition.
And the second stage Merlin engine has ignited.
Standing by for fairing jettison that has protected TESS on its way through the atmosphere. Just seconds away from jettison.
Seven, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Status of stage 1.
Stage 1 propulsion nominal.
SpaceX Falcon 9 is becoming
Power and telemetry nominal.
vehicle is supersonic. Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket, the status of stage 1.
Stage 1 propulsion is nominal.
And the SpaceX Falcon 9 has begun the pitch kick maneuver. Just about 45 seconds into flight of the Falcon 9.
Power telemetry nominal.
Just over 1 minute, the Falcon 9 will reach transonic speed and pass through max Q. That's the point where mechanical stress on the rocket reaches its peak.
Vehicle is supersonic.
And the vehicle is supersonic. Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket, status of stage 1.
Stage 1 propulsion is nominal.
The SpaceX Falcon 9 has begun the pitch kick maneuver. Just about 45 seconds to flight of the Falcon 9.
Power telemetry nominal. Transonic speed and pass through max Q. That's the point where mechanical stress on the rocket reaches its peak. Vehicle is supersonic.
And the vehicle is supersonic.
Vehicle has passed maximum aerodynamic pressure.
Just about a minute away from the next major milestone.
Begun.
Main engine cutoff, you'll hear the call MECO. That happens about 2 minutes, 30 seconds into the flight.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket, status of stage 1.
Stage 1 propulsion nominal.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system. Two, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX asset commentary.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX asset commentary. Let's get what they call outside.